So let's continue. Membranes, active and passive transport. So, what is a membrane? Biomembrane represent the amphiphilic or amphiphatic molecules of phospholipid compounds with hydrophobic tail. 3/4 of length consist of fatty acid residues, one of which is saturated and the other is unsaturated, with carbon double bonds, and hydrophilic head. 1/4 length consists of glycerol phosphorus acid. Membrane proteins can be located on the surface of a lipid layer, as you can see in this picture. In this case, we call them peripheral proteins. They can held mainly by electrostatic forces, sometimes passing through the lipid layers. In this case, we called it integral proteins, and they can form the protein channels. Surface proteins occupy 75–80% of the membrane surface. Some of the protein channels can form system of selective channels or can function as ion pumps and regulate the electrochemical system of cell excitation. The diameter of these channels is estimated to be 0.35, 0.8 nanometers. Membrane can provide such function, mechanical function. They create a barrier between the cells and surroundings and provide a relatively autonomous functioning of the cell. Barrier function. The membrane provides selective function, regulates passive and active metabolism of the cell with the environment. Transport function. The membrane coordinates and regulates biochemical and biophysical processes in the cells. The membrane provides the adhesion, the conglutination of the cells during the tissue formation. Reception function. Other cells and substances can be recognized through the membrane. Membranes take part in nervous impulse propagation. The membrane represents the environment where our bioenergetic processes such as generation of biopotential, oxidation, phosphorylation, and propagation of nervous impulse can take place. The membrane can be considered as some sort of parallel plate capacitor where the electrolytes of external and internal solutions with immersed heads of lipid molecules can be presented as plates, and the dielectric is a non-polar part of lipid molecule. So we can apply for finding the capacity of parallel plate capacitor, which is biomembrane, the formula of the known formula for parallel plate capacitor, where the electric constant equal to such value, and epsilon is the electric permeability of membranes equal to, because 2 is value for lipid. S represents membrane area and D distance between capacitor plates our membrane thickness. The capacity of membrane in average is about 0.5 10⁻⁶ farad centimeter squared. From the above consideration, the thickness of linear part of the membrane of unit area can be estimated starting from this formula, and we obtain such value, 3.5 nanometers. In this table, you can see the main physical properties of membrane, the range for thickness, for surface capacity, for electrical tension and rest, for breakdown voltage, for electric field strength. As you can see, we have rather strong electric fields, surface tension, and so on. The membrane can be presented as a liquid crystalline state. When we have change in temperature in membrane, there are phase transition. At heating, we have melting of lipids. At cooling, we have crystallization. That means that the lipid layer turns to a gel. As we consider the transport function of membrane, the first we should consider passive transport, which does not require any external chemical energy. Passive transport occurs due to diffusion, which caused by the difference in concentration in the case of non-charged molecules and by the difference in electrical chemical potential for ions. Diffusion represents the spontaneous permeation processes of substance molecules from region with higher concentration into region with lower concentration. In this picture, you can see the main types of passive transport. A simple diffusion, when we have a penetration of molecule of solvents through membrane directly, transport through the channel as we have for sodium ion, facilitated diffusion, and example is for potassium ions, and token passing. Diffusion processes can be presented as a spontaneous motion of matter along the concentration gradient due to thermal motion of molecules, and this brings the system to equilibrium. As you can see in this picture, the initial state and equilibrium state. Simple diffusion is a non-specific and very slow process, and it really depends on the size of transfer molecules and their concentration. To describe the simple diffusion, we can use Fick law, which shows that the particle flow density J is proportional to the diffusion coefficient D and the concentration gradient nabla C, which give us derivative of concentration by distance. And here is you have such formula. The sign minus indicates that the flux density is in the direction of decreasing of concentration. It should be noted that Fick law equation can be applied only if the driving force is the difference in concentration. If we replace our concentration gradient by ratio or difference between concentration and membrane thickness, what we have? The concentration of particles, if we presented this change in concentration by such graph, on the membrane surface undergo a jump due to different solubility of substance in the aqueous phase inside and outside the cell, and in the wall layer inside the membrane. So here we have lipid surrounding. So we have this jump, which is ruled by a proportional relationship. We have such ratios, which always equal to K to the partition coefficient of substance between the membrane and aqueous phase. The partition coefficient of substance is the ratio of concentration at the boundaries of our media. So we can replace our concentration gradient in Fick's law and obtain such simple expression where P represents the membrane permeability coefficient. And obtain formula provides us a description of passive transport of uncharged molecules across the membrane. What about the case when the driving force of passive transport of passive across the membrane is the gradient of chemical potential? Then we can use Thurl's equation instead of Fick's one. So here we have such equation where du pro dx is chemical potential gradient. Sometimes we can write it in such form where U represent the ion mobility and consisting of this value D divided by RT. The function of chemical potential decrease in section AB as it is shown in the picture, so its derivative will be negative, and flux density J will be directed to the right, and its projection on the axis will be positive. Then, if we consider the chemical potential for electrolyte solution in presented form, then we obtain Nernst-Planck equation with two terms. The first terms describe free diffusion and the second give us migration of ions in electric field, and depending on relations between gradients of concentration and chemical potential, we have different situations, as you can see in these pictures. When these concentration gradients will be the same in absolute value but have different signs, there will be no flow of matter at all. Our flow equal to 0, and this state corresponds to the biomembrane in the unexcited state. Then, what is channels? Channels put information with diameters of about 6 to 10 angstrom, and they cover 0.1% of membrane surface. There should be emphasized that channels are not static but dynamic formation, and according to Marlin's hypothesis, those ions which radius with one layer of water molecules is close to the radius of channel pass through the channels best, and this is the criteria for permeability of channels for different substances. One of the type of passive transport is filtration, the motion of substances through the membrane under action of gradient of hydraulic pressure. The filtration rate is found from Poiseuille equation. Here we have this formula, but here we have L as pore length, and we represent volume of filtered liquids. The formation of primary urine in the renal nephrons occurs as a result of filtration of blood plasma under action of blood pressure. What is important in such consideration? The process of unilateral diffusion of solvent molecule through a semi-permeable membrane, osmosis. If we consider biological cell membranes with thickness of less than 0.01 micrometer, pass solvent molecules that have small diameter, for example, water or oxygen, and do not pass solid molecules such as salts, proteins, sucrose, and other large protein molecules. The penetration of oxygen through the thin wall of the alveoli into the capillaries of the lungs is due to osmosis. Also, this process partially provides the penetration of nutrients from the digestive system into the blood and the action of many medical substances. Osmosis can be considered as simple diffusion, but the driving force, we choose the osmotic pressure, and osmotic pressure or the solution depends on the concentration and solute temperature, so-called Van Gogh equation. And here is isotonic coefficient, which shows how many times the number of dissolved particles increases during the dissociation of molecules. And for non-electrolytes, we have isotonic coefficient equal to 1. Osmotic pressure for human blood is 7.6, 7.8 atmospheres. The rate of water transfer across the membrane can be found from the equation, and here we have P1 and P2, osmotic pressure of the solution on the both sides of membranes, and K represent the coefficient of permeability of the membrane. Water will enter the cell until the difference in osmotic pressure inside and outside the cell becomes equal in numerical values. Then passive transport, another type of passive transport across the membrane in the presence of carrying agents or facilitated diffusion through the channel. If we take facilitated diffusion compared to simple diffusion, it is more specific and faster processes, and it is possible with the participation of a channel, for example, channel for potassium, for calcium, for manganese, a carrier, so-called promerases from permeate to permeability, which is a family of carrier proteins that increase permeability membranes for certain substances. In particular, glucose transporters, ionophores, antibiotics capable of forming a channel, for example, gramicidin, which penetrates the protein membrane through and forms a channel through which sodium ions can move. And for facilitated diffusion, we have processes of saturation, as you can see in this picture. Here you can see examples of ionophores on the example of valenamycin and gramicidin, which can integrate into membrane surfaces, form transmembrane channels, and provide the penetration of sodium, gramicidin, and potassium valenamycin ions. Then, as for active transport is forced transfer of molecules and ions from the region of low concentration to the region of high concentration. Transport system that create the required concentration gradients are called PAMs or ATPases, adenosine triphosphate. There are two main system of active transport: sodium-potassium pump, calcium 2+ pump, hydrogen pump, and proton transfer during the work of the respiratory chain by mitochondria. Then the concentration of potassium ions inside the cell is 240 times higher than in external environment, and for sodium ions, on the contrary, outer concentration is 220 times higher than inner one. According to the theory of Hodgkin, Huxley, and Katz, the cell membrane at rest penetrated only for potassium ions. So positively charged potassium ions diffuse along the concentration gradient outside the cell, forming a negative charge on the inner surface of membrane and the positive charge on the side. When the concentration of potassium ions outside and inside the cell becomes the same, the resting potentials become zero. The state in which the flux of ions along their concentration gradient is balanced by the membrane potential is called the state of electrochemical equilibrium of ions, and we can find the value of membrane equilibrium potential as follows. Rest potential is the potential difference between cytoplasm and the surrounding in a normally functioning unexcited cell, which is due to the difference in ion concentration on both sides of membrane. And the cytoplasm of unexcited cells has a negative electrical potential relative to the extracellular environment. Action potential is the potential difference which occurs when the cell is excited and is caused by the changes in permeability of membranes for ions. So, when potential difference is applied to membrane, the membrane permeability for sodium ions increases. These ions enter the cell As a result of this, the inner surface of membrane change their sign from negative to positive, and membrane depolarizes. The change in the potential difference between the internal and external environment, which occurs during the threshold excitation of the cell, is called the action potential. During pulse generation, the sodium channels closes and the potassium channels open. The potassium ions escape, and this leads to restoration of the negative charge on the inner side of the membrane, and this is repolarization of membrane. At rest, the exoplasm has negative charge relative to environment. The rest potential is about 18 millivolts, and threshold excitation has potential equal to minus 50 millivolt and action potential of plus 40 millivolt. And here you can see such a scheme of above mentioned in the picture. Sodium ions entering the cell during action potential growth can escape only due to work of sodium-potassium pump. After action potential, there is a period of non-excitation of absolutely refractory period during which the next action potential cannot occur. This period lasts from 0.5 to 2 milliseconds. During this time, due to the work of sodium-potassium pump, the initial values of sodium and potassium ion concentration are restored. So the formation of action potential is caused by two ions flow through the membrane, which is shifted in time. Along with passive transport, in the cell membrane there is transfer of molecules and ions in the direction of greater electrochemical potential. There is transfer of molecules in regions of greater concentration. This transfer of matter is not due to diffusion. The sodium-potassium pump works due to energy of hydrolysis of ATP molecules with the formation of ADP molecules and inorganic phosphate. Sodium-potassium pump transfers 3 sodium ions from the cell to the environment and exchange the transfer of 2 potassium ions into this cell. And this creates and maintains a potential difference on the membrane. The inner part of the cell has negative charge. Here you can see the scan of these processes from first to sixth stage, and then our stages are repeated again. When we speak about excited membrane, we can propose equivalent electrical circuit of excited states like we have in the picture. Here we have electric circuit with parallel branches, and one branch contains electrical capacitor and other reproduce the sodium-potassium conductivity of membrane and conductivity of outflow. Here resistance R characterize the inner solution cytoplasm and outer solution in large quantities, so it depicted as conductor with resistance. According to this consideration, the opening and closing of ion channels causes a change in membrane potential, and so membrane excitation can be described by the Hodgkin-Huxley equation, where Cm d phi m dt capacitive current associated with change in potential difference, Im ionic current through membrane, Cm membrane capacity. I potassium ions current, sodium, ion currents, and IY source current. And the current in each such branches of circuit can be presented by such formula with GI membrane conductivity for given ion and phi total potential on the membrane, and phi I represent the equilibrium potential of given ion. So that is all. Thank you for your attention.